Hello everyone and welcome to Rebel Way. My name's Andrew Sutherland and today we're going to be covering this cloudscape along with some hero clouds, and this project was created by Michael Elton Widjaja, who will be taking you through the tutorial himself. So without further ado, let's jump into the tutorial.
Hello everyone. Today I'm going to explain the cloudscape setup that I've done for one of my personal projects. The cloudscape setup will be divided into 6 parts. First is the Cumulus cloud generation, and then the instancing points, then the Skybox cloud, atmosphere, scene assembly in Solaris, and rendering the USD file and denoising with a command line render. This is the setup for the instance Cumulus cloud. I use cloud nodes mostly for this setup from Houdini. There's no custom node or anything special about it. I start with the cloud shape generate, and in this case I'm using the cloud species Cumulus, and then I added a bit of a point noise, positional noise, and then I do a cloud shape replicate to instance more spheres based on this base geometry. Merge it together, and then VDB from particles. I have 2 VDB from particles here, but this one is just a high res, the one that I use for caching, and this one is just for preview for now, so it's faster to process. And then I put a cloud adjust density profile. To check what's happening here, you can enable this visualize density, and you'll see the density inside the clouds as well. Right now, the densest part is at the edge, and then the interior part is a bit less dense. And you can adjust the fall off and the density here from the edge thickness, edge density, and fall off as well. In this case, I just leave it as it is. And then I applied a global billowy noise, cloud billowy noise. I put some expression on the offset because I want to have 10 variations of the cloud. So I just added with $F so that I can get a quick variation. I also put the $F in the shape offset at the cloud shape regenerate as well. And then I use a cloud billowy noise. This is applied globally. From the default setup, you should get a very interesting pattern already. The only thing that you need to change are, of course, the element size and the amplitude. And all the other thing, like the gain, contrast, it's optional depending on your need. And I also put $F on the offset because I want to have 10 variations of the cloud, so I can cache frame 1 to 10, and then we have a different variations of it. This cloud billowy noise is applied based on the mask, and the mask is based on the second input here. If I disable this, you'll see that it only applies on certain area. To make the mask, I'm just using the bound node and basically convert it to VDB, some noise to it, and I'm just renaming the field from density to mask. It's a float fill, and then put it as a second input. And if I disable this, you'll see the difference. Some area stays the same, some area changes. I expand the bounding box a bit because the next stage is to add the wispy noise. And this wispy noise, depending on how you set it up, it might need a pretty big padding on the for the volume. So For the wispy noise, I only applied on the bottom part of the clouds with the mask, and also I applied based on the SDF of the cloud as well. So in the wispy noise node, you can input the SDF on the second input, and the masks where to apply the noise on the third input, the same as the cloud billowy noise. So for the mask itself, I'm just using the bound node again, but I'm just taking the bottom part of the mask, just based on the Y position of the voxels, and I, as usual, convert it to mask. And for the SDF, I'm just put a convert VDB node and convert VOC to SDF. And this is what I get. Same thing here. I put $F on the offset so that I can make some variations. The thing that you need to pay attention in this node is the mask here. Make sure it's checked, so we use the masks to apply the noise. And then iteration and substep, those are pretty important to get a pretty smooth wispy noise result. And all the other parameters is pretty much the same like a normal noise parameters. There's this wind section that you can add so that you can get this streaky cloud shape moving towards certain direction. In this case, I put it to 100, means it's gonna get advected in the x-axis only. And then for the second part of the wispy noise, I just apply it globally with a mask. So the mask is very similar to the mask that I applied for the billowy noise. It's just a bit more denser. And I also used the SDF again from the newly advected cloud from the wispy noise. I expanded as well, just in case we need more room for work. And then we applied the wispy noise. This is just to get a bit of details so that we have like the area that is like very dense, and then the area that is like very wispy where lights can scatter. It gives a nice contrast between the denser part of the cloud and the lighter part of the cloud. And then some post adjustment, I kind of reduced the density a bit on the bottom part of the clouds here, just a tiny bit, so we have more light scattering here. And then this is just optimization thing. I'm just making sure there's no very low density value. So if there is, then set it to 0. And then I deactivate everything, make sure it's 16-bit, and I cache it. And this is the high-res result of the Cumulus cloud, and I have 10 variations of it. And if you want to view the clouds like more accurately in the viewport, you can always put a volume visualization node and set the occluded color to be white and the exposed color to be black, or maybe like other ambient colors, maybe like a dark blue or something. And you see that you get a pretty nice representation of the cloud in the viewport if you want to see if you have enough details for the clouds. After I cache the high-res cloud, I also make multiple levels of LOD. The first LOD, I set the voxel scale to 2 times the original size. And then second level, another 2 times, so it's 4 times the original size. And then 8 times the original size. And then 16 times the original size. And I cache everything separately as well. Once that's done, we can go to the LobNet. So the goal is to make a USD asset that has multiple variants of the cloud LODs. So say like cloud 1 will have LOD 0, 1, 2, 3, 4. cloud 2 will have LOD 0, 1, 2, 3, 4, and each of the cloud will be in a different USD file. So in order to do that, we use the add variant node to add all the LODs into one asset. So this is the first cloud, and I have the original resolution here, and then the first level of AOD, second level of AOD. You don't really see much difference here in the viewport, but once you get to the LODD, you'll see that it's getting much low res and LODE. And we add all of that into a variant here. Make sure the name of the variant is set to LOD. This is an arbitrary name, so you can change it to whatever you want. I set the primitive path to cloud hero underscore OP digits so that it will take this number. So this is the cloud hero 1. And the variant name, make sure you set it properly as well. So for the first LOD, I set it to LOD 0, and then second LOD, LOD 1, 2, 3, 4. So in total, we have 5 LODs, including the original resolution of the cloud. And for the default LOD of the variant, for the default variant, I always set it to LOD 0, the highest resolution. And then I cache it out. I cache the USD into a file, into a USD file. And I just do the exact same thing for all 10 variations of the cloud here. Once that's done, to import it and check if it's working, we use a reference node. So we will reference the USD file that we generate from the USD ROP here. If you check it, it should show you the LOD 0 variant. And if you go to the variant settings here, you'll see in the variant, it says LOD 0. And if you want to check all the variants inside the asset, inside the primitive, you can use explore variants. And you can adjust the spacing as well to see to space out each of the variants so it's easy to see. And you see this is LOD 0, 1, 2, 3, 4. So we know that it's working. And we can also set the variant manually if we need to do it for a specific shot, maybe for artistic direction or some sort. If I change it to say LOD 1, you'll see that it becomes higher res, and then LOD 3 becomes lower res. Now we know that this USD asset is working well. That is it for the instance. Make sure we bless everything that is outside of the camera frustum, and also for the points that is too far from the camera. And these are the points that we're gonna use. I created an ID attribute, random p scale based on the ID, random orient attribute in the y-axis. So since we want the cloud to only rotate using the y-axis, if you dive in here, I'm just taking the ID attribute, add some seed here if you want to change the seed of the noise, and then plugging it to random to generate a 1D output from 0 to 1. I fit it to minus 180 to 180 degrees and make sure to convert the degrees to radians, because the quaternion angle here will take radians instead of degrees. If we don't have this, it will still work. It's just that it's hard to make it controllable because usually we always calculate most of the rotation in degrees anyways, so it's easier. And then make sure the axis is set to 0, 1, 0 so it only rotates based on the y-axis, and plug it into orient. And to test if this works or not, just instance test geometry. In this case, I use rubber toy, and you see that the rubber toy has a different orientation, but it only rotates in the y-axis. Once that's done, I just make a LOD attribute. Anything that is very far away, we set it to the lowest resolution, and anything that is closer, we set it to a higher resolution. In this case, we only have the two green LODs and the blue LODs. The blue LODs is the lowest resolution, and the green LODs is the second lowest. Once that's done, I split each of the LOD and set the LOD attribute. So I split the white color. In this case, I don't have any white color, and set the LOD to 0. Split the red color. I don't have the red color as well, but if there is any, I set the LOD to 1. The green, I set the LOD to 2. And the blue, I set the LOD to 3. And we merge it all, and we export it as a USD. So the USD will only contain the points where later on we will instance the clouds. For the clouds that is present in the entire environment, I use the Skybox node. And before doing the cloudscape setup, we need to import the shot camera first, because this cloudscape setup, which is using the Skybox, is based on the camera frustum. And also there will be some LOD setup as well. So like the clouds that is close to the camera will have a higher resolution than the one that is very far away from the camera. If we want to do it for each of the shot, we need to do it in this way, because or else we need to cache one gigantic volume which has a lot of voxels, and it will be very heavy to be rendered in each of the shots. So this will be a bit different for each of the shot, but in general, the looks of the cloudscape should be the same. So here I have the HDRI that I use for render. I don't really use this because we're gonna set it up again in LobNet later on. And we have the camera. And let's dive into the cloudscape section. So first what we do is we set a grid where we want the cloud, and then I subdivide it so that we can do some colorization based on the distance from the camera for the LOD. I move it down a bit and then I colorize it based on the distance from the camera. It's pretty simple. I'm just getting the camera position here, and then here, and then I trail it if there is any movement. In this case, I have movement. Make sure you time shift it till at the end. Make a curve out of it, and now we can calculate the distance of each of the point to the curve. So the white one is the highest resolution, and the red one is LOD1, and then LOD2, and then LOD3. And you can adjust this accordingly, of course. And then I promote the color from point to primitive. And I make sure to just keep the area that's inside the camera frustum. So this camera frustum mesh, it's also very simple. I'm just using the volume node, and then put the camera in here, add a bit of padding. In this case, I just put 0.1 as a padding in each of the box here. Make sure you have the proper Z-far as well, depending on how big your scene is. Then volume bound. I trail it and time shift it at the end to capture the entire movement of the camera. Convex hull, and that's all. This one is exactly the same as this one. It's just that it's a smaller size of it. It's just with a lower Z-far. Maybe if we need to use it in a different setup or something. You can ignore this and this. Next, we're gonna split it based on the color of the primitive here. So the first one, we just want to keep the white color one, which is the highest resolution cloud. Make a bound out of it with a bit of padding. Same with the red one here. I just keep the red one, make a bound out of it. And then the green one. And then last one is. So if we merge all of this box together, we will get this. And you see that there's some area that is overlapping with each other, like this box here and this box here. We're gonna solve this later on, but it's a pretty easy fix. With this bounding box, you can put it into a skybox and generate cloud out of it. For each of this LOD section, it's pretty much the same exact setup, except for one minor difference, which is this part here. This is to fix the overlapping section of the bounding box that we seen just now between the LOD 0, 1, 2, and 3. So with this box, we can generate the clouds with the Skybox node. So we have three types of clouds: the alto cumulus, the stratus, and the nimbus stratus. Each of them has different characteristics. The alto cumulus has a very puffy shape. The stratus has a very wispy shape, and the nimbus stratus is almost like a haze, very blurry. There's no details at all. So the bounding box can be connected to the third input of the skybox here. For the alto cumulus, this is what we're looking for: very patchy and very like puffy clouds. I temporarily reduced the voxel size here. The original voxel size, I set it to 1 for the LOD 0. And the stratus is very wispy like this. And the nimbus stratus is very like blobby without details. It's just to fill in certain areas so it doesn't look too empty. Once that's done, I mask the clouds with the frustum. You can see that there's a clouds outside of the frustum right now, so I just mask it out. I'm taking the camera frustum geo boolean intersect with the box that I use for the skybox. Convert it to volume. Make sure the volume is either 0 or 1. So in this case, I'm just making sure if there is any density, or if the density is above 0, make sure to set it to 1. And then I just sample the density from the second input, which is the frustum, and multiply it with the current density, and you get this. And make sure to deactivate any 0 voxels. And I kind of mask it with a very low frequency noise just to give a bit of breakup, so it's not too uniform across the board. It's not too visible from this region because it's a very small region, the region that is very close to the camera. But once you work with the bigger skybox, you'll see the repetitiveness of the noise pattern. So this is why I do multiplication with very low frequency mask, or sorry, very low frequency noise. And then I deactivate it again, and then I post multiply the density by 100 and make sure it's in. For LOD1, I'm just copying this Skybox nodes from the LOD0 to LOD1. The only difference is the voxel size here. And we should try to keep the noise seed the same as LOD0, because later on we will need to merge it with the Skybox from other LODs. If we don't keep the same noise pattern, then you will see some harsh edges later on when you render it. So once you make the Skybox, we need to make sure that the area that is already present in the previous LOD shouldn't be generated. There should not be cloud inside there, because we already have the clouds from this LOD0 Skybox. So I'm just taking the box from LOD0 here, convert it to volume, and just multiply it, and you get this mask here. And if I merge this together and disable the bounding box, you should see that it's blending pretty well. Like, you don't see any harsh edges at all. But if you if you somehow make changes to the noise of the seed of the noise pattern, then this noise pattern won't match at the edges of the Skybox. That's why I want to keep it as it is. And we do the same thing here. We just mask based on the frustum, and then deactivate all 0 voxels, and then mask with a very low frequency noise to get some breakup. And then make sure to deactivate again, and if there's any 0 voxels. And post multiply the density. And I pretty much repeat all of this. Once you cache out the Skybox, I also prepare a proxy geo, just in case if we need to use it for like blocking the shots or something. So this is the Alto Cumulus. This is the Stratus, and in this case the Nimbo Stratus is not visible from here. But if you check the other LOD1 for example, this is the Alto Cumulus, Stratus, Nimbo Stratus. You see there's a very dark blue patch here. So when I view it from the camera, let me just disable this limit resolution. LOD3, LOD2, LOD1, and LOD0. So for the extra very far background clouds that is tricky, I'm just taking the LOD3, which is the furthest LOD from the camera, and then I kind of resize the bounding box a bit, size it, scale it down in the z-axis, and then I'm taking the Nimbo Stratus setup and just apply it here. So we don't really care how it looks from the top side, because we just want to see the streaky part from the camera, which is like this. And then I make sure to kind of multiply it in the z-axis, so it kind of fades off at the front edge of the clouds here. That's pretty much it. And I'm just like post multiplying the density again by 10 and then cache it out. It might not look like much from the camera view right now, but after the render and after you deep merge it with all the other elements, it will give some extra kind of like contrast of the shapes basically. And I have 2 layers of it. So this one and this one. For the atmosphere pass, I started with a box and converted to VDB. I'm just putting a volume visualization node for better preview. And I separated into 2 sections here. The first one here is the global atmosphere. And the second one, it's like an atmosphere that is at the edges of the scene. The reason I split it is so that I can get a pretty dense atmosphere at the edge of the scene so that you don't see the very harsh horizon line. So first I masked it based on the height. Let me just put it on using a dark background. So I mask it based on the height of the volume. And then I just add a bit of noise pattern. This is just a density multiplication with the AA noise. Nothing special about it. And then I reduce the overall density by quite a lot. You don't see that much here because the original density is pretty dense. So like if I disable this, you see it's only black, but if I view it under light background, it's actually a very dense very dense volume. That's why when I reduce it by quite a lot here, it doesn't show anything. But when you render it, it will be there. And then I make sure to deactivate 0 voxels, convert to 16-bit. And that is all for the global atmosphere. And for the second part, still the same thing. I mask it based on the height. But I added an extra VOB where I remove most of the atmosphere near the center of the scene. The center of the scene is where I animate my shot most of the time. So if you view it from the camera, you'll see that it's pretty thin here and pretty dense at the edge. And I added a bit of noise as well. Same deal. I just multiply the entire density with some noise pattern. And I post multiply the density by 0.0002. Not visible here, but when you render it, it will be there. If I disable this, you will see the density here. There you go. Same with this. Once that's done, I just combine it. And that's my atmosphere pass. Very simple. Now we're gonna assemble everything in LOPS for render. I'm using Karma XP to render the cloudscape, and then I denoise it. First, we start with the configure layer to set up the scene frame range and the frame per second. And I drop down some primitive nodes to initialize some of the hierarchy or scene graph. And then we import the camera from the Alembic that I imported in Houdini. So I'm using the scene import camera and just put the camera path here from the OBJ level, which is located here. We need to put this render camera object. And then I just rename the render camera to, previously it was called render camera. So I just rename it to render camera. And then I cache it out as a USD. So now we have the camera here. And then I make sure to import it as a reference. For the lights, nothing special. I just drop a dome light with a HDRI as the texture. I will provide the HDRI in the project files. Now we have the dome light and the cameras. And then we're gonna import the environment. So this terrain will be provided to you. And for the atmosphere of the cloud, I put it together with the environment in this case, but it's up to you if you want to put it together with the cloudscape primitives. And then I just rearrange some stuff here to group everything underground. And I offsetted the location of the entire environment to my likings. In this case, I rotated it and kind of move it in z-axis. And this is where we applied the material for the environment. The only thing that you need to pay attention is the atmosphere the atmosphere shader. So here, if you dive into it, there's a matte atmosphere. What I did for the atmosphere material is I start from the Karma cloud material and I just tweak it from there. So if you see the Karma cloud material compared with my atmosphere material, it's pretty much the same except for a couple of parameters, which is the density, which we will need to adjust depending on your scene. And I kind of reduce the shadow density a bit so that we don't block a lot of lights with the atmosphere, and increase the smoke brightness a bit. And then here I assign the material for the terrain, and then this one I assign the atmosphere material. And then I merge everything back together into the main branch. So now if I test render this, you should see the environment and the atmosphere together with the texture and shader. Next, we import the cloudscape itself. So there's two sections of the cloudscape. There's the Skybox cloudscape and the instance cloudscape. So the instance one is just the Cumulus cloud. So we do the Skybox first. Actually, it's pretty straightforward. I'm just initializing some of the scene graph primitive, and then I import all of the volumes that I generated previously from the setup, from LOD0 to LOD3. So LOD0 will be the most foreground clouds. The Cumulus cloud is a puffy one. Stratus is this wispy clouds. And then Nimbus Stratus is a very thin, hazy clouds. And then I put it under the Cloudscape Skybox scene graph here, under the LOD0. And I do the same thing for LOD1, LOD2, and LOD3. So now we have the entire cloudscape here. And I also added some extra very far background streaky clouds just to break the puffy pattern or the blobby pattern of the clouds. If you pay attention here, there's like a very dark streaky clouds in the viewport. That's the one that I am adding manually for this shot. Then next we make the material, the shader for each of the cloud type. And as usual, I started with the Karma cloud material, and then I just adjust it depending on the needs of each of the clouds. I didn't change much except that I checked the use secondary anisotropy to get some like very nice like specular on the clouds. And then density scale will depend on your density field of the clouds. I don't want to assign the same I don't want to assign the same shader for all the clouds because I want to be able to control like how wispy maybe the stratus layer is, how wispy the nimbostratus or something like that. I don't think I use this Flocus Skybox material, so you can ignore this. And here I assigned it. Also, just another tips. You can check if you assign the material correctly into the primitive by clicking this gearbox and select material, and you'll see the material assigned here. And if it's empty, then it means it's not assigned properly. You can also assign it on the parent primitive, and it will inherit the material from there. But in this case, I assign it directly to the volume because each of the type of the clouds needs to have a different shader. Then after it's done, I merge it back to the main branch together with the environment. And the last part is the instance clouds. So first of all, I import all the cloud variation, the Cumulus cloud variation here. I import the USD file that we generated before in the Cumulus cloud setup, which has multiple variants in it. So we have the LOD, the LOD0 variant, and then 1, 2, 3, 4. So we're gonna use this this variant later on. And in this specific shot, I have two sets of setup here. This is like a manual placement, which is very specific to this shot that I'm working on. Let me just view it here so I can see it from the camera view. So it's just for these two clouds that I specifically placed there. And then we have all the other clouds that I just like instance randomly. I just scatter some random points and just instance. So first we merge all the available clouds. So now all the 10 clouds variation are in this scene graph. Make a collection out of it. I call it var for variation. And I make sure to set a separate instancer for each of the LOD. In this case, I only have, from the point that I scatter, I only have LOD 1, 2, and 3 available. So I just set everything to LOD 1. And then here, I believe I don't have anything in LOD 1, so we can ignore this. And in LOD 2, first of all, we set the entire clouds to LOD 2. And then we drop an instancer node. And inside the instancer, I'm just loading the USD file that has the cloud, that has the point cloud for the cloud scatter. So the green one is the LOD2 and the blue one is the LOD3. And we don't have the red color one, which is the LOD1. That's why we ignore LOD1. And after that, I make sure to just apply to the point group of LOD2. So now we only instance a couple of clouds here. For LOD3, we have a lot more since we have a lot of blue points. It's a bit slow, but there you go. And right now it's instance randomly. Like it doesn't. I don't have any attribute that controls like which point should correspond with which cloud or something like that. It doesn't really matter because like since it's pretty far away, we don't really need like a very specific clouds or placement or anything. So once that's done, I merge it together with the cloud that I placed manually, and then assign the same material that I use in the Skybox, and merge it together with the entire scene. So now when I view it from the camera, there you go. Everything is there and ready to render. Once that's done, we set up the Karma render settings. I have like multiple settings here for low quality, mid quality, and high quality. At the end, I override everything. So this only applies for like all the other element beside the cloudscape and the atmosphere, because those two render paths takes very long to render if we put too much pixel samples. So we really to get a almost noiseless render, I really depend on the denoiser itself from Karma. This is just a switch between all the quality of the render settings, and this is for adding overscan. In this case, I use 0.05 as a padding. Switch for overscan. And now for the render part, I split it into the ground, which is just the terrain, the atmos, which is only the atmospheric, and the cloudscape. And I separate the very far background cloudscape in a different render path. This is entirely up to you. You can always just render it together if you want to. And I render it with deep, so like I only force phantom everything, and I didn't do any like holdout. So here, this section, I'm just pruning everything and try to keep the ground only. I think at the end I didn't use the force phantom from the clouds, so that the cloud can cast shadow, but it's too heavy to render that kind of stuff, since it's a sunrise or sunset. Maybe there's not much shadow that is being casted by the clouds, not like during the midday. So in this case, I can get away with just rendering the terrain without any shadow from the clouds itself. And then here I set up I already set up the pixel samples before in the Karma render settings, but certain element I kind of force it to render always with this pixel samples. If I disable this, then it will use whatever pixel samples that you've set in the render settings before that. For the atmospheric, I just isolate the atmosphere. It's not really that visible here, but it's there. And yeah, I didn't use the cloudscape as a phantom as well for this, because it's too heavy to do it. So I just rendered the atmosphere alone. I might have used... No, I didn't use the ground as well for force phantom. So it's literally just the atmosphere. And I set the volume step rate of the atmosphere to 0.1 to get a faster render, and path trace samples to 64. We can get away with this because the atmosphere in general, we don't really have like details. It's more about like hazy stuff that can scatter lights. If I render this with Karma XPU, there you go. That's the atmosphere. For the cloudscape, I think I also render it by itself without any force phantom at all. So this is the cloudscape, and I set the render pixel samples to 64 for faster render as well, because cloudscape render is infamous for being heavy to render, and there's not much ways to get around beside doing some optimization in the cloudscape scatter itself, like setting up the LOD and only cache the clouds that is inside the frustum. So the denoise will take care most of the render noise, so that should be good for 64. Maybe in some cases you might need to bump it up to like 128 or 256, but just be aware that even in Karma XP it will take a while to render. So if I try to render these. Yeah, these are the clouds, looking pretty cloudy to me. And this is the very far background clouds. And once that's done, I just put a switch node and I render it the same way that I rendered the vapor jet in my previous tutorial. And yeah, that's pretty much it. You can choose to render the image directly or export the USD and then render it from the USD instead. It's up to you. To render the cloudscape, I'm using the USD method instead of rendering it directly from the LobNet. First, I put the switch node, and this switch node will take all of the render passes as the input, and I will use the pass attribute that is being made from the context options editor. So the naming right now for the input name is environment ground, environment atmos, cloudscape, and cloudscape extra background. In the context options editor, you can make this custom label by clicking the add a new options here. And we're gonna add a string menu because it's going to contain the render passes that we're gonna render. So once you made the label, you can double click it to rename the label itself. In this case, I'll rename it pass2 since I already have the pass. And for the item inside the label, the value, you can click the pass2 and then click this edit the properties of the selected option. You can decide what item or what string should be in there. The string, I put the name of the render passes that I will render. Once you click this edit option, you can change the name of the item inside it and the value. Since we're gonna use the name of the render here in the name, and we want the value to match exactly with the name, then we can just do the automatically generate values, so we don't need to input it twice. So first I call it cloudscape, and then we're gonna render the cloudscape extra background, and we can add more. We're gonna also render the environment ground and the environment atmos. Once that's done, right now the pass2 is empty, but if you click the drop down menu, you can decide which value should be inside the pass2. And with this context options editor, you can actually set what pass we should use for the switch node. So we drop a edit context options, and then the context options name is pass, which is taken from the context option editor here. This pass here, or pass2 if you're using pass2, but in this case, I'm going to use the one that I already created. And we set the pass value to the tops pass attribute. We're going to generate all the USD file from tops. So instead of like switching one by one and cache the USD manually, we can tell Houdini to cache all the input one by one separately into a different USD file. And this is just setting up the quality and the overscan. I created a context option label called quality and overscan. And once that's done, you can drop a USD ROP to cache the USD file. Or if you decide to render it directly from LOPS, you can drop a USD render ROP instead. I'm using the USD ROPs. And make sure the frame range is correct. And now we dive into the top network. The top network is pretty straightforward, but it's a bit tedious. You just need to put a wedge node in the top net and name the attribute tops underscore pass, because this is the attribute that we're using to pass the value into the pass attribute of the context option editor. So tops pass, we retype every single passes that we're gonna render. In this case, I don't need all of this, so I can just remove. So we only have four passes that we're gonna render. And once that's done, you can directly connect it with a rob fetch node. And when you right click and select the dirty and cook this node, this will generate the USD file into the specified path that you set here. So here in the output file, I put it under $heap USDS shot the shot context option. If you go to the context option editor, I have a context options label called shot, and inside it, it's the shot number. And then RN, just short for render. And then tops pass, which is the tops pass that we created inside here, tops pass. .usda. You can choose between .usd or .usda. USDA is just the ASCII version of the USD file instead of binary. The advantage of using .usda is you can inspect it in the notepad or other text editor to check the content of the scene. The downside of this is the file size is gonna be much bigger than .usd, but it's up to you. Once you set up the output file path, go back to the top net, link the ROP that you drop in the LOPnet here, which is the USD ROP, and then you can right click and dirty and cook this node, and this will generate the USD file into this path here, and it will, every time it goes to the next pass, it will change this value as well. So now you're gonna have a separate USD file for each render passes. In the top net, I have a couple of nodes called filter by expression. This filter by expression is to render specific passes from this wedge pass here. So say you only want to render the cloudscape extra background. What you can do is you compare the string between the current tops pass, basically the pass that we're iterating on, and if it's the same as the cloudscape extra background, then it will keep it. So I set the operation to keep matching item. So if I cook this node, you'll see that at the start you have 4 work items, but after it goes through this filter by expression, it only has 1 work item. And if you middle click it, you see the tops pass is called cloudscape extra background. This is useful if you want to render specific passes, and instead of deleting or adding manually in the wedge pass, we can keep this as it is and just filter it out. You can also have multiple expression if you want to render like 2 sets of render. Say you want to render cloudscape extra background and also the cloudscape layer. You just copy this into here. I'll delete the other and change it to cloudscape. If you cook this right now, it will not create anything because right now we set the expression here to n. It means that the tops pass must match this and this naming, which is impossible. So make sure you set the expression to OR. And now if we dirty and cook this node, you have two work items going through, and it's called cloudscape extra background and cloudscape. And you can connect this to the rough fetch and cache it out if you want to just cache two of this USD file. So the result will be something like in this directory here. You can see that I have some other render passes here, but this is what we're going for. Each of this USD file is for rendering that specific element. Say I want to render the aircraft, and this aircraft may have like a force phantom with the clouds or something like that. Everything is already set in here. So to render this, we can run the hash command in the console or command prompt. To render this USD file with the command prompt, you can create a CMD file. In this case, I call it usdrender.cmd. If I open it with a notepad, this husk console command is used for rendering the USD file. And in this case, it takes path. And because I put the CMD file in the same directory as all the USD file, I can use the dot, means it will search the current directory and then render this cloudscape extra background.usda. You can manually set the start frame and the end frame as well. I'm sorry, this is not the start and end frame, but this is like the starting frame and how long from the start of the frame to render. So if I set this to like 51 and render with a frame count of 150, it will render from frame 51 to 200. Engine, since we're gonna use Karma XPU, we set it to XPU. Make output path is just to make sure that if the directory doesn't exist, Houdini will create one for you. Verbose is just for logging purposes. And this rem at the start of the command here is to basically comment out the lines that you don't want to run, since I just want to run it for certain render passes. Once that's done, you can save the CMD file and close it and just double click this, and it will open a console, and you will be able to see the progress there. After you finish rendering it, the render will be pretty noisy because the pixel samples that we set to render the cloudscape are pretty low. So now we're gonna move on to the denoising part. I'm denoising it after render instead of during the render. So in order to denoise it, you can go to the render passes. You can go to the folder of the render. And based on my setup, I generate two separate folders here. The deep, which contains the deep data, and primary, which contains the normal EXR with all the AOV. And if I view this render, the primary render, and load it, you'll see that it's very noisy. To denoise it, I'm using a command file as well called denoise primary. So this primary underscore denoise folder is being generated by this command here. I have this command in each of the render passes, and if I open this in a notepad, I have this. It's actually a pretty long command, but it's just the AOVs here that I put. So what the command does is that first it will create the directory called primary underscore denoise. And then what this is saying is that for each of the EXR in the primary folder, run this idenoise command. This idenoise command comes from Houdini as well. I believe it's using the Intel OIDN denoiser. For each of the EXR file, make the same file under the primary underscore denoise with the same name. And this part determines the denoiser, which is the OIDN. And in order for the denoiser to work, we need to provide the albedo and the normal AOV. So A is the albedo. I set it to albedo. That's the default AOV name in Houdini for albedo. And N is the normal. I set it to N. EXR mode, I believe it's something related to how it's being compressed. I set it to 0 by default. And AOVs is all the AOV that you want to denoise. Because certain AOVs, certain utility AOVs, you shouldn't denoise because or else it will not be usable for comp. Something like the position pass or the normal pass or the UV pass. So we only want to denoise anything that is related to the beauty pass or something that contributes to the beauty pass. In this case, it's the color, albedo, any diffuse, emission, reflection, volume, transmission or transparency, and all the indirect stuff as well. And once that's done, then you can close the command with a parenthesis, save it, and close this, and double click this, and it will open a terminal or a console, and then you can see the progress of it making the primary denoise version of the EXR. Some area the details can become a bit too blurry or smudgy, but I feel like this is a good trade-off between quality and render time.